Hello all. In this lecture, we will try to take up some problems, basically the knowledge modeling problems, and we'll try to see how we can represent the requirements specified in natural language statement into its corresponding OWL structure. Right. So we'll be using the OWL vocabulary to represent knowledge stated in natural language. So we will be having different cases, and going forward we will also like to highlight different kinds of errors that people generally make when designing one OWL knowledge base from a natural language specification. Right. So until now, in the last lecture, we have seen different constructs, and the specification of the examples, we have used the RDF XML syntax, right? And you know that RDF XML syntax is kind of, it's pretty elaborate, and the structure is really little bit bigger for a given statement. So instead of using this RDF XML syntax, we will like to use some other syntax which we call functional style syntax specification. So which follows the functional programming paradigm. So it follows the functional programming paradigm. So everything is represented using function, right? We will not talk about a formal specification of this functional style syntax, which you can find in this embedded URL. But the syntax is relatively simpler. As we work with these examples, we'll get to see the syntax that we are talking about, right? So when we talk about the errors that we do in modeling, so they can be categorized into different categories. The first question that is relevant when we define the concept. So mostly when we represent something in OWL, we define different concepts based on their relation with other properties and other, right? So in that concern, we have already seen that we can define a concept to be one equivalent class with other class, or it can be a subclass with other class, right? So given the specification in natural language, we need to first decide whether we should go with equivalent class like definition or subclass related definition, right? So that is the first decision point. And the second thing that we always forget, that nothing is implicit. So even though the reasoning or kind of logic that is very intuitive in human realm, but it may be not that apparent when we do the inference using programs or machines, right? So we should not take things to be implicit. So you need to make everything explicit, and from this explicit representation, we'll be coming up with sounding, right? So one such case of implicitness or explicit definition is related to class disjointness. So if you have defined, say, one male class or a female class, but you see that in more generic sense or more intuitive sense, you'll take this male and female class to be disjoint with each other. But that should not be taken as granted. So whenever you are defining classes and you want the classes to be disjoint, you have to explicitly tell whether the classes are disjoint or not. Otherwise, they will not be taken as disjoint implicitly, right? We have talked about open world assumption in a short in the last class, and this open world assumption is really a very difficult concept to grasp as far as the semantic web logic is concerned, and there are very curious scenarios that will be happening, and we need to be very careful about something that relates to open world assumption. Whenever we use the Boolean combinations along with the quantifiers. So we know that there are basically different kinds of quantifiers. For example, you have these all values from, some values from, or has value, all those sort of things, right? Now you want to combine them with Boolean operators, right? So there the meaning of the things will be kind of changing depending on how you are placing these combinations, right? So for example, you have say sum not and not sum. So sum not is completely different from, so this is a completely different, having completely different semantics than not sum. So whenever we represent something with sum not, that will not mean not sum or vice versa. So you need to pick up the right combination depending on the situation. Either it should be sum not or not sum, right? Similarly, all values from, not all values from, or all values from not. So all these things, they can uh, be bit intriguing, and you need to really put forward detailed thought how to and what to use, or what combinations to use to model your scenario, right? Now, the first decision point is whether you want your class definition to be equivalent class definition, or the subclass type of definition. So, whenever we talk about these kind of classes, the classes you define in OWL, they can be categorized into two types. One is a defined class, and other is the primitive class. The defined class is like you have a defined entire thing about the class. So whatever you have to say about the class, you have already said. So it is a kind of, you are having a very close definition. So and that's why you want to represent that using equivalent class, right? So basically, for defined classes, you already know all the necessary and sufficiency condition of something to become a class, or a particular class, right? And that is exactly modeled with the equivalent class construct in OWL, right? On the other hand, in primitive class, you leave some scope to be defined later, right? So this follows this. Here you encode the necessary condition of something to belong to a primitive class, but you do not specify the sufficiency condition, and this will be modeled using subclass. So as we have seen earlier, whenever we say that a class is a defined class, so there we'll be using this both way implication, because both way implication stands for this necessary and sufficient condition. But whenever we talk about subclass, they come with this forward implication, which is basically talking about the necessary condition, but not the other way, which is the sufficiency condition, right? Now, coming to the equivalent classes. So let us have some examples where we define the classes to be equivalent class. Now, there will be certain cues in your statement which will help you to decide which kind of formalism you want to use. So, for example, if we try to model this, the cheesy pizza is any pizza that has, amongst other things, some cheese topping, right? So, what would be our decision point? Whether to use equivalent class or subclass? To answer this, let us look at certain keyword like say in. So we're saying that cheesy pizza is, you pick up any pizza, right? But the other added property to that is it will be having some cheese topping, right? So it is a kind of completing the definition of a cheesy pizza, right? So in that sense, you want to use one equivalent class representation here. So it is a kind of any pizza that has, among other things, has some cheese topping. But again, this definition, whether you are going with an equivalent class definition or subclass of definition, there is not really a very hard and fast rule. It's entirely depend on how we are trying to model the thing, whether you want to make it bit open, this definition bit open, so that you can include something more later, or you want to make it very close. So you have all, you know that this is going to be your definition and you want to freeze this definition at this point of time, right? Now, let us try to come up with the owl representation of this. So, as we have mentioned earlier, we will be using the functional style syntax. So, I will not be writing down the RDF style syntax, which we already know how to do. But again, the software tools, they will be taking care of that. But for the sake of understanding, we need some syntax like functional style, right? So now we have got equivalence of two things. One is cheesy pizza. So this is one class. The other class is comprising of the other part, right? So equivalence relation or equivalence class definition has got two parameters. The parameters are basically you are defining equivalence of two class definitions or class expressions, right? So the first class expression is cheesy pizza and the second class expression is something else, right? So in functional style syntax, this is how we'll be proceeding. So equivalence, equivalent class. So you say two classes are equivalent. So this is the keyword in functional syntax. Equivalent classes, because we are having two classes. So it is a kind of function. So whatever we will be defining in functional style syntax is through a function, right? So the first thing that we are defining is the cheesy pizza. We are defining cheesy pizza to be equivalent to something. And what it is equivalent to? It is equivalent to something that is pizza and has some cheese topping, right? So it should be an intersection of the pizza class, assuming that we have a class called pizza and other class which has got some cheese topping, the set of elements that have got some cheese topping, right? So it is a kind of, so cheesy pizza is a set which is equivalent to another set which is the set of intersection of pizza set, right, and set of the other things which has got some topping some cheese, right, has some topping to be cheese. So this is a kind of, so we have got one set here, the other set, right? So we need to have as our second argument for this equivalent class to be the intersection of these two sets. So we need to take intersection of two classes, and the keyword for representing intersection in functional style syntax is object intersection of again it will be what it will be consisting of. It will be consisting of a set of lists, right? So the set of or list of classes, right? What is the first class here? It's pizza. So intersection of pizza. And what is the second thing? The second thing is that, so it has some topping. So I'll not say has topping some ways. So I should, if we try to put it in a correct way, has some topping cheese, right? Now we'll try to model this using has topping property, right? So basically we will be modeling it with has some topping to be cheese. So we'll be using some values from restriction. So this we are modeling as a restriction class, right, as we did earlier. Now this restriction class has got two things. One is on which property, right, and the on which property part is has topping, right, and what kind of restriction. The kind of restriction is some values from, And what is the value? Value is cheese, right? So this is how we'll be modeling. So the keyword to represent this all sum values from or all values from is basically object sum values from. Object sum values from, right? Now then we'll be presenting, so this is the restriction type of restriction, and on which property you are putting the restriction? We are putting the restriction on has topping. And what is the value we are restricting to? The value is cheese, right? So we are closing this bracket, closing this bracket, and closing this bracket, right? So this is the functional style definition or representation of the statement that we have presented here, right? And you see that there is an equivalent RDF statement, and we'll be having a demonstration session where we'll be seeing that whenever we represent something using this equivalent or other classes, what would be the corresponding RDF construct. So we'll talk about that later, right? Now let us try to represent this using first order logic syntax, right? So so the first thing that we can think of, that this is one equivalent classes description, right? So we'll be having a both way implication, right? So the thing that we are trying to define will be in the left hand side of the implication, right? So we are defining for all p, the p is a cheesy pizza, pizza p, right? And as we are defining one equivalent class, it will be intersection of pizza and the other thing, right? So it should also be a member of pizza. Sorry, p should also be a member of pizza. And now let us model this sum values from, right? So the way to model sum values from, that you assume that there exists at least one topping, right, where has topping pt is 2, and along with that t should be a member of cheese class or type of, t should be a type of cheese, right? So this is how we can represent this particular representation using first order logic form, right? Now let us move to the so I think, yeah, so you have the, let me remove this drawing. So this is the corresponding RDF XML form of the statement that we have written in functional style before this. So basically I'll just do it for this particular example, but going forward we'll be using only functionals. So we are defining cheesy pizza to be equivalent to another class, right? And this class is an intersection of a collection of classes, and the intersection consists of pizza to be one class, the other class is a restriction class, and the restriction is on property has topping, and the kind of restriction that we are imposing is sum values from, which is existential restriction, and the restricting value is cheese or cheese topping, right? So this is how we are representing the same thing in RDF XML, right? Now coming to so this we have already done, right? So this we have already done. Now coming to the case where we can define something using subclass of formalism, right? So let us try to model all margarita pizzas have, among other things, some mozzarella topping and has also some tomato toppings. So here, I'm not really saying that these margarita pizzas, they are pizzas. I'm just saying the margarita pizzas have some mozzarella topping and some tomato topping, right? So this margarita pizza is a kind of subclass of the set of things that are having some mozzarella topping and also some tomato topping, right? So this is what we are trying to say, right? So let me try to draw it. So you have this margarita pizza here, and this is the set of elements that has some mozzarella topping plus has the tomato topping. Now you can be having say one sandwich that might be having say mozzarella topping and tomato topping, right? But so what we along with this pizza, so this margarita pizza, they are becoming a subset of this. So this particular set, which is kind of set having the elements that are having this mozzarella topping as well as tomato topping, this will include the margarita pizzas which are having this mozzarella topping and the tomato topping, as well as it may also contain say sandwiches, right? So in that sense, margarita pizza is a subclass of the thing that are having some mozzarella topping and some tomato topping. So let us try to model this, right? Now, so again, we'll be using the functional style syntax, and the functional style syntax to represent subclass is you just use this keyword subclass of. So you use subclass of, right? So this is the keyword for represent something. Again, you will be having two classes. So C1 is a subclass of C2. C1 is a subclass of C2. So margarita pizza. So this is a subclass of something that is having mozzarella topping and some tomato topping. So you are having one and here, so that's why we need to model this as intersection. So object intersection of two things, right? So the first thing is some mozzarella topping or some has some mozzarella topping, and we will be using the has topping thing again, right? So object, so as we are using some, we will be using object sum values from. Object sum values from, right? And what it will contain? It will contain again the property on which we are imposing the restriction as topping, and the value would be mozzarella, right? And what is the other class? Again, similarly, it will be object sum values from, sum values from has topping tomato, right? So we are closing this, and closing this, right? Now, how do we represent this in first order logic? Again, as we are having subclass, we'll be using the forward implication, right? So we say for all pizza, this P belongs to margherita pizza, P, if, now you need to model this, right? How do you model this? So there exists, say T1, right? There exists a topping which is a topping of P, or P has topping this, P has topping T1, and of course this P has topping T1, and this T1 should be a instance of mozzarella. So it is an instance of mozzarella T1, right? So this is the representation of this, and we need to model intersection, right? So we take the intersection, and the second part of this we will be modeling this, right? So there exists T2 as topping PT2, right, and tomato T2, right? So you know that we are having this corresponding first order logic representation of this functional style syntax, right? So I guess we have the RDF representation. And now let us try to model it in a different way, right? So in the earlier representation, so let me go back to this. So we had two objects some values from, and we had got two statements related to this. Now one might wonder that can we say something that object some values from has topping mozzarella and tomato, right? So what we are trying to say here, so we want to model it as, so this MP is a subclass of something has topping, has some topping tomato plus mozzarella, right? So the corresponding functional style syntax representation would be subclass of margarita pizza, objects of values from has topping, and you are taking intersection of mozzarella and tomato. So you are pushing this intersection inward, right? Now what will that mean? So this will mean, so you have something X, right, and it has got has topping, right, which is basically say Y or say T, right? And what is T? T belongs to, so it is a type of something, some class which is equivalent to the intersection of mozzarella and tomato. Now you are trying to take something, find out some element, find out some topping that is a type of both mozzarella and tomato, which is not really possible. We cannot have any element, any ingredient that is both mozzarella and tomato, which is basically represented, being represented using this, right? So you want some topping T which is both mozzarella and tomato, and that is not exactly the thing that we are trying to model. So that's why this is an incorrect representation of the statement which we have made here, right? So here we have not really mentioned that it has got some topping that is a tomato as well as a mozzarella, right? So this would be representing something like that. So all margarita pizzas have, among other things, some topping that is both mozzarella and say tomato, So this is the representation for, so this particular structure you can see is the representation for this statement, but for not for this statement, right? So we need to be very careful. So this can be coming out of intuition, that we can take the intersection of this mozzarella and tomato and make that to be the value for these some values from restriction. So we need to be careful in this kind of scenario, right? Now, how do you state the fact that vegetable, meat, seafood, cheese, they are all disjoint? So you know that for that we'll be using all disjoint classes. So we are saying that this vegetable, meat, seafood, cheese, these classes are disjoint with each other. So for that we need to use this all disjoint classes, right? Uh, mm, Now the functional syntax way to represent this is basically you say disjoint classes vegetable, meat, seafood, cheese. Very simple. Now, how do we model this? A dog owner is any person who has uh, pet some dog, right? So here we can see that a dog owner is kind of the persons who are having some pet dog. So we have a sense of necessity and the sufficiency, right? So if uh, uh, someone is to be a dog owner, that thing should be a person and also should have a pet to be something that is a dog. But the other sense is any person who has a pet some dog is also a dog owner, right? So you have both this necessary and the sufficiency condition. So you can model this using the equivalent class formalism, right? So again, how do you model this? So equivalent classes, right? So dog owner is the class which we are trying to define, right? And it will be an intersection of person and the other property. So this will be represented using one restriction class, right? And it will be taking the intersection of these two, right? So dog owner object intersection of, right? And the intersection would be between person, right? And what is the other thing? So you have got sum, so you'll be using some values from restriction, right? So object some values from, will be having has pet as the property on which we are putting the restriction, and the value, the class to which the value should be restricted. So this is the class to which the values for this property will be restricted, right? Now, what will be the corresponding first order logic representation for this? So for all p, so we have for all p, right? So p is a dog owner. P is a dog owner. We are using the equivalent classes, both way implication. P should be a person, right? And there exists something, say D, where P has pet to be D and D belongs to dog class, right? Now, how do we model this? So, a first class lounge is any lounge where the occupants are only first class passengers. So, here as we are having, you can see that we are having this necessary and the sufficient condition both are to be met. So, this will be represented using equivalence class. So, we don't have any confusion on that. Uh, but there is something else. So you have got only, so you need the occupants of this particular thing or occupants or the things on where the occupants are only first class passengers, right? So we are having the sense of only here, and we know that how to model this only. So all the values, so you will be using this has occupant. So let us see what would be the structure of this particular representation or statement. So let's say you have say one establishment E, right? And this establishment has occupant. So occupant to be say O1, right? And this might have another occupant to be O2 or maybe other O3, right? Now this O1, O2, O3, if say let us say O1 is of type say first class passenger, right? And O2 is also type first class passenger and O3 is also type first class passenger, right? So in this case E, so we are defining one anonymous class say CA here, right? So in that case E would be belonging to this class, which is representing where the occupants are only first class passengers. So all the values you can see in the range position of this particular property for a given subject, if all the values they are restricted to a class which is your FCP, then this particular element would become a member of this anonymous class, right? Now let us think about another situation where this O3 is belonging to another class, for example second class passenger, right? So in that case you cannot say that E, so in the change scenario E does not belong to CA, because you have got at least one instance where the occupant is belonging to a class which is different than FC. So we are assuming that these two are disjoint. This SCP and FCP, they are disjoint, right? So this scenario will be modeled using this only, and only is represented in OWL using all values from, right? Now how do we write this? So equivalent classes, and we are defining first class lounge, right? So first class lounge, right? And it is an intersection of a class which is lounge, right? So we'll be using object intersection of the intersection between lounge and the restriction class, which is your CA, right? And how do we represent CA? We are using all values from restriction, right? So object all values from, right? And the restriction is on say has occupant, right? And the restriction would be on the so the values would be restricted to the class, the first class passenger, right? So we need to close this, and so this is the representation of this particular statement in functional syntax. And let us try to come up with the corresponding first order logic form, right? So for every passenger, for all passenger, it will be designated as first class passenger, right? P. Oh, we are defining first class lounge. Sorry. So we should use, say, let us use a different symbol, say L, right? And we are defining first class lounge. Lounge. L is a first class lounge. We have equivalent classes. We'll be using both the implication. Lounge. L should be a lounge, and also for all the occupants, like the passengers, right, has occupant. So L has got occupant to be P, and this will imply that this P is a first class passenger, right? So this is how we can represent the same thing in first order logic. Now we'll be combining this for all with some other concept. So here we are trying to define vegetarian pizza is kind of any pizza which among other things has only vegetable and or cheese topping, right? So here the other part is very easy, but the anonymous class description we need to think a bit carefully, right? So let us try first draw the visualization for this, then we'll be going to the functional scene, right? So we are defining this anonymous class, again we are naming it as CA, right? Now, so let's say you have got one, say, element E, right? And it has got a topping, has topping, right? Say T1, right? And T1, either it is a vegetable or a cheese. So either it is belonging to the class veg, right? You can be having another as topping, say T2, which is of type say cheese, right? Now if you had a description like, say, has only vegetable topping, remove this cheese part, right, has only vegetable topping, in that case E would not be referred to, E would not be the member of CA class. So if we have crossed this, so this we are saying that a vegetarian pizza is any pizza which among other things has only vegetable topping. So in that sense E would not be a member of this CA, right? But as we are saying that has only vegetable or cheese topping, so this T1 is a member, T1 is a member of union of veg or cheese. T2 is also a member of veg or cheese, right? Now let's say we have got another such information, say T3, another topic has topping, and T3 has type to be say meat, right? And I am assuming that they are all disjoint, right? Now if we have put this, then E again will not become a member of this CA, right? Because this T1 is belonging to veg union cheese, T2 is belonging to veg union cheese, but T3 does not belong to veg union cheese. So that's why in that scenario, in the change scenario, E3, EE would not be a member of CA, right? So with this, let us try to define the concept vegetarian pizza using OWL functional, right? So we'll be using, as we have done, equivalent uh, classes structure, right? So equivalent classes, equivalent classes, and you are defining veg pizza, right? And it is an intersection of pizza and the anonymous class, which is CA, right? So object intersection of, and the intersection is between pizza, let me indent it a bit more, pizza, and the all values, we will be putting one all values from restriction, right? So object all values from, all values from, right? And the uh, restriction, we are putting restriction, the restriction would be on hash topping, right? And what would be the value? The value would be basically the intersection of veg and cheese. Sorry, the union of veg and cheese. And how do you take that union? We will be using object union. Object union of veg and cheese. Right? So we close this, we close this, we close the intersection, we close the equation. Right? Now, let us again, as we are doing earlier, come up with the first order logic representation of the same thing, right? So, for all P, veg pizza, P is veg pizza, if pizza, P is a pizza, and for all topping, if P has topping to be T, that implies either P is veg or P is cheese, right? So with this, let us stop now. In the next lecture, we will be coming up with more examples with more change scenarios. Thank you very much.